Ratio.
Wait a second. Do I still?
Okay. I know that.
Okay, favorable over.
Favorable
Okay,
over
please
outcome.
don't blurt. Favorable over.
Total.
Caden.
Okay. Somebody favorable over
Total.
total. Okay. Total possible outcome. And then we did probability that is theoretical versus probability that is experimental. And what is the difference between those two? Can somebody tell me?
Experimental is the results.
Okay, experimental is based on results, and theoretical is based on what is supposed to happen, what should happen, right? Okay, so first thing, when we have probable, okay, when we talked about flipping a coin last lesson, right? And when we talked about flipping a coin, and we based it, if I made, let's say 7 tails, if I flipped it 10 times and I got 7 tails, okay? Then is there actually a 70% chance that I'm going to get tails on the next one? Yes or no?
No.
Could be yes, could be no, depending on what? Depending on if I'm going by experimental probability, if I'm going on theoretical, right? If I'm going on experimental, yes, there's a 70% chance. If I'm going by theoretical, no, there's a what?
50-50.
50% chance. Okay, good. So what we're going to first start with today, okay, this is compound probability. Okay, so your objective is to determine compound probability of events. Why aren't you writing this down? Okay, to determine, okay, compound probability of events. Okay, now this is, how many of you have ever heard the word compound before? I know you've used it in other classes. What does compound typically mean? What is the definition of compound? Somebody?
Like
Yes.
kind of like many smushed together.
Okay, kind of, yeah. It's basically, okay, probability was the likelihood of an event happening, right? Right? Okay, compound probability is the probability of 2 or more simple events, okay? The probability of 2 or more simple events. Okay? Now they can be the same event or they can be different events. If I am rolling a number cube and I'm flipping a coin, are those 2 simple events?
Yes.
And I'm finding the probability of both of a result happening that's that combines both of them. Okay, does that make sense? So let's just say, well, look at example 1. Okay, let's look at example 1 here. Okay, and this is easy, guys. This is really easy. Okay, 2 number cubes, 1 red, 1 blue, are rolled. Okay, so what was important about that? You know, 1 red number cube, 1 blue. They're both 1 through 6 are fair dice, right? Okay. What is the probability that the outcome of the red number cube is even? Okay, now, what do you see? This word right here. And. Is that important?
Yes.
If I said in order for you to win $1 million, you have to flip a tails and roll a 5. If you flip a tails, did you win the $1 million?
No.
If you just roll a 5, did you win $1 million?
Yeah.
You have to do what? Both of those things have to happen, okay? So what we're going to do, and when we're determining this, okay, what time do I have till? Oh, I got oodles of time. Okay, I'm going to find the probability of each one of these independent events, okay? Does rolling a number cube, does that affect what I get on the other number cube?
No. Nope.
Doesn't have anything to do with it, right? So what is the probability on the red number cube of getting an even? How many evens are there?
3.
There are 3 out of what?
3 out of 6.
Out of 6, okay, which I can simplify to what? 1/2. Okay, now this is the probability of the first event. Okay, this is of the red even. Okay, now the probability of the second event was to get a blue 5. Okay, on the blue number cube to get a 5. Well, how many 5s are there on the blue number cube?
Just 1.
There's 1 out of how many possible outcomes? 6. Okay, so this one is 1 out of 6. So these are two completely different probabilities. They're independent of each other. But I want to.
Mr. Kersey,
Yes, ma'am.
can you please send Noah Arnholt to the office with his belongings?
Yes, he's on his way.
Don't go to your locker. Just come with what he has.
Okay.
Thank
Go.
you.
No, here's your worksheet, buddy. Okay. All right, listen. Yeah, hurry. Okay, listen. So what I want to know is this question is asking what is the probability of both of these happening? So what do you think I'm going to do with those two independent probabilities? Good guess. I'm not going to add them.
You're gonna compare them?
I'm going to multiply them. Okay? So I'm going to multiply them across. Okay? So I take these two probabilities once they're simplified and I multiply them straight across. And you remember if you multiply fractions, do you cross multiply? No. You go straight across. What's 1 times 1? 1. What's 2 times 6?
12.
Okay, so if I roll both of these number cubes, I would have a 1 in 12 chance of getting an even on the red and a 5 on the blue. Okay? Make sense? Okay, let's look at example 2. I told you guys, this is easy. Okay, look at example 2. All right. There are 6 black socks and 4 white socks in a drawer. Okay, so let's think for a second. Do you think that it's going to be important on how many socks there are?
Yes.
Yeah, there's 10 socks, right? Okay, so if there are 6 blocks, now this is an example of dependent probability. Okay, why is that? Because if a sock is taken out without looking, and then a second is taken out, okay, did I put that sock back?
No.
No. Okay, so if I take something out, do you think that affects the probability?
Yes.
It absolutely does, okay? So first of all, how many socks are there? There's 10 socks, right? There's 10 socks. 10 socks. Okay. Now, I want to know if I am taking, I want to know if one sock is taken out without looking, then a second, what's the probability they'll both be black? Okay. First probability of getting a black sock. Okay. How many black socks are there?
There are
Guys, how many black socks are there?
6.
There are 6 out of how many?
10.
Out of 10. Now, can I reduce this?
Yes.
Yes, to what? Bless you.
3/5.
3/5. Okay, now, the second probability is another, we'll call it the second black sock. But something has changed. Okay? I took one of the black socks out, didn't I?
Yes.
So there are no longer 6 black socks. How many black socks are left?
5.
There are 5 black socks. But there are no longer 10 socks. How many socks are left?
9.
9. Okay, so I'm going to take this probability, and then I'm going to multiply it times this probability. Okay, this is an example of dependent probability because this depends on what? On this probability. Does that make sense?
Yes.
In other words, one probability affects the other one. So I'm going to multiply 3/5 times 5/9. Now, if you guys remember, when we multiply fractions, there's some things I can do to make it easier,
Cancel.
right? Cross
Cross
canceling. If these are both 5s, they become what?
1.
1s. And then does something go into both 3 and 9?
Yes.
3 goes into 3 how many times?
Once.
Once, and 3 goes into 9 how many times?
3.
3. 1 times 1 would be 1. 1 times 3 would be what?
3.
I would have a 1 in 3 chance of pulling out a black sock first and then a black sock second. Okay? Does that make sense?
Yes.
Yeah? Okay. Pretty simple stuff,
Would
right?
that be the answer? 1 and 3?
Yep, it would be 1/3. Okay, the last one, okay, a card is drawn from a deck of 10 cards numbered 1 through 10, and a number cube is rolled. Now, let's think for a second, okay? There's 3 different ones here, but these are easy. Are these dependent probability? Does the card I pull out have anything to do with the number cube that I roll?
No.
They are not. They're completely independent. So all I have to do is find the probability of each one and do what?
Multiply.
Multiply them, okay? What is the probability of getting a 10?
1/10.
1 out of 10. What is the probability of a 3?
1 out of 6.
1 out of
10. 3 out of 6. 6.
Okay, hold on. How many 3s are there?
1.
1. But, this doesn't, oh, sorry. This is a probability, okay, I should have read this better. This says this is the probability of drawing a number out of 1 through 10 and then the number cube. So this is 1 out of 10, but this 3, how many 3s are on a number cube?
1.
1. But it's not out of 10, how many numbers are on a number cube?
6.
6, 1 out of 6. Okay, so if I multiply these, what would be my answer?
160.
I would have a 1 in 60 chance of pulling out a 10 and rolling a 3. Okay? Do you want me to do these other two examples, or are we good to go on this? It's pretty easy, right? You want me to do them? Okay. So the probability of getting 2 even numbers. Well, how many even numbers are on a numbers 1 through 10? 5 out of what? 10, which can reduce to what?
1.
Okay. 1/2. How many even numbers are on a number cube? 3 out of 6, which can reduce to? What's 1/2 times 1/2? 1 times 1 is 1, 2 times 2 is 4. Okay, and then this last one, try to follow the arrow, sorry. Okay, 2 prime numbers. Okay, so if I go through numbers 1 through 10, how many of those are prime?
4. 1.
Let's think about this. 1 is considered neither prime nor composite, so we're not going to count that one. Is 2 prime?
Yes.
Yes, that's 1. Is 3 prime?
Yes.
That's 2. Is 4 prime?
No.
Is 5?
Yes.
Is 6?
No.
Is 7?
Yes.
Is 8?
No.
Is 9?
No.
Is 10?
No.
Okay, so how many primes?
4.
4 out of how many? 4 out of 10. Can we reduce 4 out of 10?
2/5.
To 2/5. Okay, this is prime. And then the second one, a prime number between 1 and 6. Well, we're not counting 1. Is 2 prime?
Yes.
Is 3?
Yes.
Is 4?
No.
Is 5?
Yes.
Is 6? No. So what is that one going to be? 3 out of 6, which would be what? 1/2. So we're going to multiply 2/5 times 1/2. And what do we get? What's 2 times 1?
2.
Uh-oh, can I do something here? Can I do some cross canceling?
Yes.
I can do these 2's, right?
Yes.
1 times 1 is
1.
1. What's 5 times 1?
5.
5. Easy enough?